Okay, welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're fortunate enough to be joined by Dave Jewitt, who's flown up on a flight that was from LA today. He had to miss his first flight, which was cancelled, so he only just made it here about 11, which is very fortunate for us all, because he's going to talk to us today about primitive bodies, primitive icy reservoirs in the solar system. Dave is now at UCLA. He did his undergraduate work at the University of London and came across to do his master's and his PhD at Caltech. In the mid-80s, he started a search for Kuiper belt objects, a systematic search, which in 1992 paid off when he found the what we now know as the second Kuiper belt object with Jane Liu. And since then he's been cataloguing more Kuiper belt objects. And from that count, I understand we're now looking at an estimate of about 70,000 objects that are out there. I'm sure he's going to tell us more about that in his talk today. So if you'll all join me in welcoming along Dave Jewitt.
Okay, so this is a broad colloquium with this title, Primordial Ice Reservoirs of the Solar System. I have this position that the colloquia that I like are the ones that give big picture. And the ones that I don't like are the ones that are hyper-detailed, because basically I can't understand them. So this is a broad picture talk. And if you want hyper details, you can ask me hyper detailed questions about this broad talk. But the point is to get across a broad picture for people who don't already know what's going on in these various areas. So I'll talk briefly about an introduction to this subject, and then I'll spend most of the time talking about these three things: the Oort cloud, the Kuiper belt, and the main belt. And certainly those are words that most people have heard in the past. I always find when I talk to astronomers, most of the people I talk to are astronomers for some reason, that they say things like, yeah, we know all about the Oort cloud, but we don't actually know anything about it. And so when we discuss the Oort cloud, they've heard the words, but they don't really have anything in their heads about it. So I'll assume that's true for most people here too. So what's happened in the last 20 years or so is that our perception of the solar system has changed in important ways. And I have this slide labeled Your Grandmother's Solar System, not to be offensive to any grandmothers or grandfathers or grandparents or anybody old, but to point out that, when I was a kid, and even more recently than that, the solar system was described in these terms. The sun, these things, the planets with famous names, including this one, and a box at the end called Other, into which all of the trash was dumped. So all of the small things, the comets, the asteroids, all the things that the artist for this picture didn't really care about, are put rather ignominiously in this box called Other. And the great irony is that in the last 20 years, many of the biggest developments in our understanding of the solar system have occurred precisely with objects that sit in that box called Other. So there's no connection between the size or the mass of a body and its scientific importance, or the information that it carries. And then the next diagram says a similar thing in a slightly different way. I think the first diagram was by the Weird and Wonderful International Astronomical Union, and this one is by the Weird and Wonderful NASA. And this is NASA's solar system. You may have seen this diagram yourselves, where each circle on this plot represents a spacecraft sent to one of these things. So you can see there's a tremendous number of spacecraft sent to Venus, the Moon, and Mars, and not very much going on with the giant planets and the small bodies out beyond them. And it doesn't mean that the only interesting things in the solar system are Venus, the Moon, and Mars. It just means they're easy to get to. Okay? In fact, they're not any more interesting than any of the other things in the solar system. It's just that we have a really tough time sending spacecraft to the outer parts. And so that opens the door for people like me and Dale Cruikshank and Noemi, who can use telescopes to study these things. We can look at places where we just can't go, and probably in our lifetimes never really will go big time with spacecraft. So I'd like to define these domains, these three domains for the solar system. First of all, terrestrial planet domain, consisting of the obvious likely suspects, Mercury, Venus, Earth, Mars, and probably the asteroids. Bodies that formed by binary accretion, and bodies which are distinguished by having primarily rock and metal compositions, just like the Earth. And they kind of form a conceptual domain in my mind because these bodies formed probably in about the same way by binary accretion. We understand quite a lot, we think, about the process of binary accretion. And they're distinguished by this common composition. Most importantly, we know a lot about the terrestrial planets because we live on one, we send sound waves through it, we've been all over it, we've visited the others nearby. And so we understand the terrestrial planet domain, we think, pretty well. Certainly much better than we understand the other two domains. The next one is giant planet domain, Jupiter, Saturn, Uranus, and Neptune. There, we have much less information because, for the reason I just mentioned, we haven't really sent many spacecraft there. We don't have much detailed knowledge, and we have all the problems of distance when we use telescopes to study these bodies. So we have basic appreciation that they're quite different from the terrestrial planets. They're compositionally different. They're primarily, at least Jupiter and Saturn, primarily hydrogen and helium by mass, a little bit like the Sun. And they must have formed by some process different from the process that formed the terrestrial planets. And we have these two basic themes, these two ideas for the formation of giant planets. Perhaps they formed by nucleated instability, where some rock ice core grows a bit like a terrestrial planet up to a critical mass when its gravity suddenly becomes strong enough to initiate a hydrodynamic flow of gas from the nebula. It just falls onto the core and makes it undergo a runaway in growth. Or perhaps the planet's formed by an instability in the protoplanetary gas disk of the Sun in very early stages. Maybe the disk was just so cold in the beginning and so massive, so dense, excuse me, that it couldn't stand up against its own gravity and spontaneously collapsed down to make the giant planets that we see. And, the consensus goes this way and that. Solar system astronomers tend to like the nucleated instability model. The planets grew a bit like raindrops growing in a cloud where the water sticks onto some condensation nucleus because, in part, detailed measurements show that the giant planets have these dense nugget cores. Particularly Saturn has a very strong, very clearly measured core. But for planets in other systems around other stars, the case is completely unclear, and we don't know which process, if either one, is the right one for forming those planets. So anyway, there's the giant planets. We know less. They formed in a different way. They look different. They have a different composition. They're more sun-like, more star-like than the terrestrial planets. And then at the end of this kind of journey of ignorance, we have what I call the comet domain, which is basically all the other stuff. And it's mostly comets because most of these bodies are cold and trap ice in some way. These bodies sit in reservoirs that, by and large, were only recently discovered and have barely been explored. And so we don't have much knowledge, we don't have much information about the comets, and we don't know a great deal about their histories. And so that's why there's a lot of activity in the last couple of decades in the study of small bodies, the things that go in that box called other in the second slide. We basically live in a state of comparative ignorance about them. So here we have what we know of the three primary reservoirs for comets. First of all, Oort cloud was inferred in 1950 by Mr. Oort and consists of a large number of objects in a spherical swarm surrounding the Sun. We'll talk about that in just a moment. We think the objects in the Oort cloud were formed in the vicinity of the giant planets, which probably were not then where they are now, maybe in this range, and were scattered out. to the Oort cloud and captured by various processes. So they're formed at temperatures probably like this, 50 to 120 Kelvin, and they've been stored in the Oort cloud nearly as cold as you can get, at temperatures like 10 Kelvin, where the temperature is just sustained by the UV flux of the background stars. So that's the Oort cloud. Kuiper belt was discovered in 1992. It's basically a ring of stuff, or a donut of stuff, beyond Neptune. Neptune is now at 30, probably was originally closer into the sun. The temperature of formation, probably not very different from the temperature now, something like 50 Kelvin in the Kuiper belt. But still cold enough to trap many, many important volatiles in icy materials in these bodies. And there was a talk a little while ago, which I watched on the web, by Dale Cruikshank, discussing the investigation of solar system ices, trapped basically forever at low temperatures. And then very recently we identified this third population, which we call the main belt comets. And people erupt with anger and furor when we say this term, main belt comets, but you guys don't care, which is good. The main belt comets are part of the asteroid belt. We'll talk about those too. They're comets which sit in the asteroid belt. So they're 3 AUs from the sun, very, very close, very, very hot, 150 Kelvin, almost as hot as you could imagine for bodies that still retain primordial ice. So those are the reservoirs that we have identified for original ice in the solar system. I'll just flash through some pretty pictures because that's a nice thing to do, NASA, all that stuff. Here are some pictures of cometary nuclei. This is the nucleus of what heathens call Wild 2 and Swiss people called Wild 2. This is a small body, 4 kilometers across, something like that. It looks to me like it's a figure of rotational equilibrium, although that statement has not been clearly made by researchers in the field. Its surface is peculiar, has lots of dimples in it, things that look like impact craters but probably are not. And it's one of several examples of cometary nuclei that we've imaged close up from spacecraft. Here's another one, similar in scale. This is Temple 1, imaged from a spacecraft which threw a projectile into it. And this object has, more evidence for craters. There's a nice one right there. Other strange surface features, including this bizarre tongue of material, which may be a surface flow of some sort, creeping over the surface of a body with an escape speed that basically is less than a meter per second or something. So a very, very strange geology, frankly not understood on the cometary nuclei. Here's a satellite of Saturn called Phoebe, which is an irregular satellite, goes around backwards relative to the spin of the planet. And this object is almost certainly captured, in fact, is certainly captured, but we don't know from where. And there are people who suggest that maybe it was captured from the Kuiper belt, in which case we would be looking at a 200-kilometer sized captured Kuiper belt object. There you go. Phoebe is a dark and dirty body, but it has ice on it. And you can see the ice when there's a landslide. The landslide exposes bright patches of ice. The ice is seen spectrally from Cassini. And this thing has a density of about 1.5, consistent with ice-rock mixture, perhaps with also some porosity. And then this picture I've been putting in talks recently, including all the ones that burned out my throat last week in Nashville, for totally gratuitous reasons. It has nothing to do with my talk. It's just a beautiful picture. I love this picture. This is like one of the best pictures ever taken as far as I'm concerned. This is a regular picture, a regular satellite of Saturn called Hyperion, 400 kilometers in diameter. It's a biggie. It has this remarkable surface morphology where the craters look like they've been made with a stick poking into the surface. And we don't know why. There's speculation that that's somehow associated with the density of this thing. It's half the density of water, so it's very porous. And then there's this awesome crater, which covers up most of the visible surface. These cliffs are about 20 kilometers. Imagine, sliding down that thing. 20 kilometers of sheer ice. It's a high albedo body, about a half. Just an incredible picture. I think over 20 kilometers you'd get up to the escape speed of Hyperion. What is that? Several hundred meters per second. I'll leave that to you. The Oort cloud, let's talk about that. So the Oort cloud is an inferred structure. We can't observe the Oort cloud directly because it's basically objects in the Oort cloud are too far away. And we only see objects from the Oort cloud when they've been deflected inwards by something. So the history is that Oort inferred the existence from a diagram like this, which shows basically the gravitational binding energy. So 0 means the comet is not bound to the sun, so it's following a parabolic orbit. On this side of the diagram, the comet is bound to the sun, it's following an elliptical orbit, and on this side, the comet is unbound, it's following a hyperbolic orbit relative to the center mass of the solar system. And Oort compiled this. I think he had 16 or 17 comets originally. Now we've added many, 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 many more, and the basic picture has remained the same since 1950, which is good and bad. It means that Oort's model is essentially confirmed, but it also means that nothing much has happened in this field, as I'll now describe. So his key observations were these. First of all, there are very few comets on hyperbolic orbits, and the ones that exist are only barely hyperbolic. In fact, they're so weakly hyperbolic that it's plausible that most of them are actually parabolic or slightly elliptical, and we simply have poor data, so we have uncertainties in the estimation of the orbital elements of these things because we have a tiny observational arc relative to the very long periods. That's one possible cause. Also, these bodies have been slightly perturbed by planets, and so we're looking at the orbits after they've been kicked a little bit, and so they could have come in elliptical and been kicked and are being sent out hyperbolic. And there's no evidence for any comet that is strongly hyperbolic, moving on an orbit consistent with coming into the solar system from the interstellar medium. Such a body would plot, far to the left of me over here. There are no strongly hyperbolic objects known yet. So that's his first observation. Second one is that this peak is quite strong, and this peak basically gives the size of the Oort cloud. Oort's observation was that the peak is strong and narrow, and he remarked that if you drop comets into the solar system from infinity, so they come in on this line, they'll be scattered by gravitational interactions with the planets, since the solar system is not a point mass. And so their orbital energy will be deflected, will random walk on this diagram. And so the fact that this peak is strong and narrow, in particular narrow, showed Oort that comets in this peak are coming into the solar system essentially for the first time, or maybe the second time or the third time, but not for the 1,000th time or the 10,000th time. So these are newly arriving comets from some place, which is the Oort cloud. The spherical nature of the cloud is inferred from the fact that these long-period comets drop in from completely random directions over the sky. Same number, northern hemisphere, southern hemisphere, doesn't matter. And that's still observationally very true. So Oort's model basically relies on almost entirely on this diagram and then some thinking that he did way back there in 1950. The number of comets in the cloud is a big fraction of a trillion. It's uncertain, but it's comparable to a trillion. And the mass of comets in the Oort cloud is even more uncertain because we don't really know the average size of a comet nucleus. We don't know the density. We don't know the mass of the average comet nucleus. But it's certainly many Earth masses of stuff. So it could be one Earth mass, could be 10. Some people would say 100. Well, I think that's doubtful. So that's the Oort cloud as we've known it for some time. The method of emplacement of bodies into the Oort cloud is by scattering outwards by the planets, as I mentioned, the giant planets in particular. If they don't absorb planetesimals from the disk, near-miss interactions cause slingshot ejection of bodies out towards the interstellar medium. And the process is not very efficient. Most things are lost to the interstellar medium. If I throw something up in the air, I have nothing particularly good to throw at the moment. Well, cookie. I was going to throw the cookie. If I try to throw this up to exactly hit, the Oort cloud represented by the ceiling, if I go too low, it falls back into the solar system. No good. If I go too high, well, it hits the ceiling and escapes from the solar system. So to get it just right is very, very difficult. And so most objects, in fact, are lost, particularly those ejected by Jupiter and Saturn, which have large escape velocities, just throw everything out into the interstellar medium. So the best guess from models is that the emplacement efficiency is a few percent, up to 10%, something like that. And the few objects which are not lost are bound around the sun by additional perturbations they receive on the way out. And Oort's idea was that passing stars do this. We still think that's the case. They also get assistance from the tide. from the galaxy, because the galaxy is this big asymmetric distribution of mass. Now, with these low emplacement efficiencies, you have to take the trillion comets that we think are in the Oort cloud and multiply it by a factor of 10 or 100. We get large numbers of objects ejected to the interstellar medium. And if those large fluxes apply to every star, you can calculate how long we'd have to wait before interstellar comets should be observed coming back through the planetary region. The answer is, well, it's a hell of a long time. And probably we won't see those, even with the next generation survey telescopes, like Pan-STARRS, if that thing ever works, or the LSST, if that thing is ever funded. But still, it's worth looking. So there's a chance we'll see one of these hyperbolic guys coming along. And when it does, we're going to launch a spacecraft, go there, and bring the thing back and study it. A sample from another planetary system. Just kidding. So, large masses of material are involved. The comets are individually small, but large masses of material were ejected to the interstellar medium and to the Oort cloud in the beginning. Oort's model is a great model, and it's been the state of the art. It does have a couple of strange things about it. The main one is that it doesn't work as a dynamical model alone. So if you take only dynamics, Oort's model predicts a much larger number of returning comets relative to first appearance comets than we observe. And Oort's solution was to invoke something that he called the fading parameter, which is a fudge parameter, basically. It's an unspecified physical process that, in his mind, made comets fainter when they came back into the solar system after having been through a few times. And so one of the big weaknesses, I think, of this model, to me, is that it has a completely arbitrary fading parameter. Oort talked about interstellar frosting. He said, comets are floating in the interstellar medium. They're going to pick up interstellar frosting. And then first time they come through the planetary system, the interstellar frosting will make them all bright, and the second time it'll be gone. But we don't know what that interstellar frosting is or whether it exists. And so fading parameter is still the major uncertainty with the Oort cloud. So research in the Oort cloud, I think, needs to address that question closely and carefully. And sometimes when I meet noble dynamicists, I challenge them by saying, well, maybe you can make a model of the Oort cloud that doesn't assume this fading fudge parameter. Maybe you can do Oort cloud just based on dynamics. And so far they haven't. So it's a tough problem. There's also the likelihood that there is an inner Oort cloud from which comets are much less easily eroded than from the classical outer Oort cloud. And this inner Oort cloud potentially could contain much more mass even than we have in the outer Oort cloud. Such a structure would be populated in early times if the sun were part of a dense stellar cluster, because then there would be more frequent and stronger external perturbations to circularize the orbits of escaping comets. Before they got out to 100,000 AU distances, they could be circularized maybe at 5,000 or 10,000 AU. And so there's a lot of work going on about the nature of the inner Oort cloud. The most important question is it populated at all? And there are some extreme models floating around now, even one that came out a couple of years ago, in which it was asserted that there is no classical Oort cloud, that it's all inner Oort cloud, but that some tricky dynamics makes it look like the outer Oort cloud comets are falling from further away than they really are. So don't think of the Oort cloud as a done deal. It's been stagnant for a long time, but it's reviving as people think about it more and more closely. Let me move on to save time to Kuiper belt. Kuiper belt is this ring beyond Neptune, as I said. It's important to us in the solar system because it's the source of the Jupiter family comets, probably. It's the sun's debris disk. It has an optical depth of 10 to the minus 7, whereas the debris disks of other stars that are famous, like Beta Pictoris, are maybe 1,000 or 10,000 times bigger than that. So it's a kind of a puny debris disk, but perhaps consistent with the great age of the sun and the steady depletion of material that you would expect to occur in some collisional system out there. And then as it's the home of the Jupiter family comets, we know that it's a repository of all sorts of interesting volatile materials, perhaps embedded in amorphous water ice, perhaps trapped in this sponge-like amorphous water ice that seems to be a stable form at temperatures below about 70 Kelvin. Stable on the lifetime of the age of the solar system. And this is really a remnant of the accretion epoch. Not a primordial remnant, it's been changed in many ways, but we can see what's been going on by looking carefully at the distribution of objects. And then here's just a picture showing how these things are identified at the telescope by their movement. Here's a perspective view. It's a bit faint because the lights are a bit bright, but you can get the idea that this thing is not a flat sheet. So here are the orbits of the planets: Jupiter, Saturn, Uranus, and Neptune. Neptune here. And then these ellipses are the projected orbits of Kuiper belt objects that define this fat donut distribution of Kuiper belt stuff out there. So it's not an accretion disk. It's dynamically quite excited. The highest inclination objects, actually one has been found that's, a couple are found that are retrograde. They're quite a broad distribution of inclinations and eccentricities in the belt. And the standard way to plot something interesting about the orbits of these bodies is semi-major axis on the x-axis from 20 AU to 100 AU, and then orbital eccentricity from 0 to 0.8 on the y-axis, so circular orbits here and elliptical orbits at the top. And it's a highly non-random distribution. So we went from this one thing in 1992 to 1,300 Kuiper belt objects known now. This is the first few hundred good ones plotted on this diagram. And you see there's a very non-random distribution of objects in the semi-major axis eccentricity plane for the Kuiper belt. I'll just say a few words about this. I could talk about Kuiper belt for hours if my voice allowed, and I have done that in the past, and I don't want to do that anymore. I'll just give you a very quick summary and move on. First of all, these red things, the classical Kuiper belt objects, seem to be long-term stable, stable for billions of years, basically because they never get close to Neptune. And that's because Neptune's here at 30 and 0. These guys are out there at 40-something, and they have eccentricities that are like 0.1. So that means they go in and out by something like 0.1 of the semi-major axis, so roughly from here to here, like that. And they never get close to Neptune, so Neptune never has a strong scattering effect, and these guys sit there forever. The vertical lines show mean motion resonances in the Kuiper belt, period resonances between the orbits of the objects and the orbit of Neptune, which is the gravitationally dominant body out there. Here's 1 to 1, 3 to 2, 2 to 1, and there are many more in which objects are known. These objects get dynamical stability by being in a special phase relationship with Neptune. So objects above this diagonal black line, for example, have a perihelion distance inside Neptune's orbit, but never meet Neptune because they are smart enough to know that they can only come to perihelion when Neptune is 90 degrees away around its orbit. Yes, they are sentient beings. They know exactly what's happening to them. And you know, the most famous one of these things is Pluto, right there. I know you picked it out immediately, right there. And that diagram simply tells you why Pluto is a dead planet.
Why is there name 1 to 1?
I'm sorry?
Why is 1 to 1 impossible?
It's not clear. The probable population of 1 to 1 is huge, actually. So it may be that the intrinsic population of the 1 to 1 resonance is bigger than the Jovian 1 to 1 population. It's not clear. In fact, the whole question of the sizes of the populations of the different resonances is very, very interesting. It's affected by many things, but comes into this idea of planet migration. So things like the speed of planet migration, the jumpiness of planet migration affect the ability to trap bodies in resonances. They'll have different strengths and somewhat different dynamics. Anyway, and then we have this big arc of bodies. These are things that are being scattered by Neptune. They have a perihelion distance near Neptune, so they're near this line, and they get weak scattering that makes them unstable on billion-year timescale. So we think this is the shadow of a much bigger Kuiper belt population. There are other populations that I can come back to if we need. So the key things about Kuiper belt, there are many things, but the key things are there's not much mass in the Kuiper belt. I mean, for all the objects that we have, the total mass is puny. It's still only 1/10 of an Earth mass or something like that. So it's a very small mass. And if you take that mass and spread it over the plane of the solar system, you know, roughly from the orbit of Neptune out to 50 AU or 60 AU or something, the surface densities in that disk are so small that binary accretion won't grow the objects we see, even given 10 times the age of the universe. And so the growth times are so ridiculously long that we need to find an answer to that problem. And the answer that seems to be most plausible is that the Kuiper belt in the past was not so weak as it is now. So we think the Kuiper belt is a remnant of a much more massive disk surrounding the sun in the early times. And people are discussing augmentation factors of 100 and maybe 1,000. So maybe we're looking at only 1% or 1/10% of the mass that was originally there. We need that kind of augmentation to bring the formation time down to plausible, reasonable values. Which raises the question, how would we lose 99% or 99% of the mass in the Kuiper belt? The other thing is what I already mentioned. We see the resonances are well populated, more than one would expect by chance. And the best and basically only idea for that is the idea that the planets were not formed where in the orbits they now occupy. So their orbits expanded, orbit of Neptune expanded at some time in the past, pushing its mean motion resonances out through the accretion disk beyond it and trapping bodies like a snowplow being pushed through the snow. So if you take these two ideas together, the fact that the Kuiper belt is a shadow of its former self and that planet migration is necessary to sweep resonances around, you can ask the following question. What would happen if planet migration happened so much? What would be the consequence of planet migration if two major planets got into a mean motion resonance? In particular, what if Jupiter and Saturn got into a mean motion resonance? And that's essentially what the Nice model tackles. So the Nice model is a numerical model of the solar system that has four massive planets, the red, white, green, and purple dots, Jupiter, Saturn, Uranus, and Neptune. Outside of that is a Kuiper belt, so this is a row of dots that represent Kuiper belt objects with a total mass in this model, I think, of 30 times the mass of the Earth. So that's an augmentation of a factor of 300 relative to the existing known mass of the Kuiper belt. And it's the same kind of plot. It's an AE plot. Here's the orbit of the current orbit of Saturn. Here's the current orbit of Neptune. So it's the relevant region of the solar system is shown. And the Nice modelers in Nice and elsewhere release the planets and follow the motion of the particles in the Kuiper belt. And the first thing is this arc is immediately thrown up due to interactions with the outermost planet. So this looks like the scattered object population in the Kuiper belt. And the planets jump around because they have recoil motions. When they eject a body, they recoil in the other direction. They're ejecting the bodies, including their mass and some energy and some angular momentum, so they jiggle around on this diagram. The flashing things are objects which are very short-lived. Nowadays we call them centaurs. They simply get shot out of the system so quickly they never appear again. We can see the beginnings of resonant structure in the Kuiper belt. Here is what looks like the classical Kuiper belt orbit distribution with the small eccentricities out beyond the scattered arc. And everything looks good until the system reaches a catastrophe in just a moment. And a catastrophe occurs when, bang, when Jupiter and Saturn get into mean motion resonance. So all through this movie, let me just see if I can go back to that. All through this movie, Jupiter and Saturn have been radially migrating. And so they're inching closer and closer to the 2-to-1 mean motion resonance, at which time they have periodic, strong gravitational interactions, and they shake the solar system, and they shake all the stuff out of the Kuiper belt. A lot of it's lost. More of it comes in, hits the sun and some planets. Some of it may be captured in various places in the inner solar system. So that's the essence of the Nice model. Now I have a quiz. I like to have a quiz in my talks these days. The quiz is, what's the difference between this movie of the Nice model and the movie I'm about to show you? Okay, ready? I have to put the microphone up to the computer to get the sound.
You know, Christy, something happened a long time ago in Haiti.
Can you hear?
And people may not want to talk about it. They were under the heel of the French. You know, Napoleon the Third or whatever. And they got together and swore a pact to the devil. They said, we will serve you if you'll get us freedom of the prince.
That's okay. I'll tell you
True
what.
story. And so the devil said, okay, it's a deal. And
So what he's saying is that the earthquake in Haiti was caused because the Haitians did a deal with the French and made a pact with the devil. And the whole thing has come back to haunt them right now, basically. And this must be true, of course, because you can tell from the woman and the serious way in which she's looking at the old man what a great font of wisdom that guy is. So what is the difference between the two movies that we just saw? Any advances, any suggestions? The first thing I should say is that the people behind the first movie are sincere people trying to understand the physical world and working hard to do that. Okay, so there's a big difference right there. I'm not sure that those statements would apply to this man. But I don't see any explanations being thrown forth. I'll just make my own. My interpretation is that actually it's hard to say because this guy has a model that fits the data very well. The data is that Haiti was destroyed by an earthquake. His explanation fits all that just fantastically. So maybe he's right. How would we ever know? Well, we would only know if he made a prediction, which he hasn't done. And so that's the trouble with the Nice model. So the Nice model looks beautiful, actually. It looks like a religious thing. It's just fantastic. Except that, it doesn't do what a scientific model has to do. It doesn't make itself observationally testable. Okay? So that's the problem. So I think we all admire the Nice model. It's the first really nice model that's kind of global in scale and describes a lot of different things in the solar system, can fit a lot of measurements taken in the solar system, but is not very good at making observationally testable predictions. In fact, I don't know of any that it's made so far.
Jupiter and Saturn will get into a 2 to 1 resonance.
No, it says that they have, but what's the observational prediction of that? How do I test it?
But they're not.
What?
I mean,
Oh, they come out. Of course, they come out. In their model, they pop out the other side. They scatter each other out. So it hasn't done it.
would the Earth survive Jupiter and Saturn?
Well, that's one interesting point. The question was, would the Earth survive this massive shaking of the solar system by Jupiter and Saturn? And the answer is that in the original model, no. It's emerged recently that the Earth would not survive, which some people take as a big hit against the model. And so they've modified the model. And so there you have it. It's not just these people. As I say, these are good people doing the best they can. It's the problem of modern science that computers got cheap, and it's easy to calculate very, very complicated models, which tend to have large numbers of poorly constrained parameters. And then the question is, well, what do we know? How do we test those models? And I really, for this case, I really don't know the answer. It's been almost 5 years, and we don't have any clear observational predictions from this model. So I heard this thing at the bottom somewhere, I forget where. It seems to me unusually cruel, but I thought I'd just repeat it anyway, just for fun. The string theory of planetary science. Yeah.
The structure that you saw at early times at 100 million years for the orbital parameters of the Kuiper object from that 30 Earth mass, does that repeat itself at later times?
The question I have to, because the microphone is screwed up, I have to repeat that. The question is, does the structure that emerged in the Kuiper belt Nice model in early times reappear later? Because it's all destroyed by the explosion. The explosion happens because a planet is dumped in the Kuiper belt and just blows everything out. Well, the answer they would say is, yeah, sure. That's what they say. Yeah. There are a number of uncertainties. The stability of the Earth is an issue, and the growth of bodies in the Kuiper belt, because it has to sit there in their model for a long time, for hundreds of millions of years, that's another issue. Anyway, I just mentioned this to you as state of the art. It's a beautiful model. It may well be correct, but I don't know how to prove that it's correct or to prove that it's not correct, because I don't know how it connects with observations that we haven't taken yet. Let me go on to the last thing, because I'm going to run out of time. The last subject, main belt comets, the third reservoir, the main belt comets and the origin of the oceans. So what's an asteroid, what's a comet? People have different ideas about that. The ideas that make sense look like this. Dynamically, an asteroid is a body with a semi-major axis less than Jupiter's and a tisserand parameter, which is this thing, bigger than 3. So Jupiter has a tisserand of 3 exactly. Asteroids are bigger than 3. Comets are less than 3, with a few arguable cases very close to 3. So if you take these first 2 criteria, this one, and take a picture of objects that satisfy both of those, you see point sources, asteroids. But in recent times, we've been able to take pictures of things which are dynamically asteroids by these criteria, but look just like comets. So those are the main belt comets. Here's where they fall. Here's the same semi-major axis eccentricity diagram, but this time on a tiny scale. So we're right down here now between the orbit of Mars at 1.5 AU and Jupiter at 5.2 AU. So this is the inner part of the solar system. The black smudge shows 50,000 asteroids from the catalogs with the Kirkwood gaps and so on in here. The blue dots are the comets. Mostly Jupiter family comets in this plot, but not exclusively. And plotted on top are these 3 other objects, which are, they have funny names like Reed, 118401, 133P. These objects are visibly mass-losing objects. They're comets by the observational definition of a comet, which is a hairy star, something that's losing mass in an unbound atmosphere. But dynamically, they sit, I think you'll agree, right down there in the asteroid belt, not up there with the comets. So what's going on? Here's a picture of the first one that was seen actually in 1996, and somehow, because it's such a strange being, didn't really get into people's consciousness until about half a decade after that. So here's the nucleus of this thing, and it emits this dust, which is swept back by radiation pressure in this long trail, which actually goes to the edge of the picture in this diagram. It sits 3 AUs from the sun, so it's quite hot. It's a mass-losing body in the asteroid belt. It's been integrated by several people, and its dynamical lifetime is, the age of the solar system. It's stable. It's not always active. The first picture was taken near perihelion. The second picture, with a bigger telescope and a higher sensitivity, shows no trail whatsoever when the thing had moved a little further away from the sun. Indicates that the activity is episodic. And we've watched it go through perihelion 3 times now. Each time it's turned on, it's lost mass, and then it, after a few months, turns off and becomes an inactive, boring asteroid again. So it behaves just like a comet. And the only explanation that makes any sense to me for this thing is that the mass loss is driven by some thermal process. It gets close to the sun, the activity turns on, gets further away, the activity turns off. And that fits sublimation. So it's probably an asteroid that contains ice in its surface regions. And here's pictures of the same thing and a couple more. If I just cut that picture out and showed you that and asked you to tell me asteroid or comet, you'd all say comet. But it's right there in the main belt. So it's an asteroid. It's both. It's a comet and an asteroid. Here's that diagram again. And here's what people, the noble individuals in the asteroid community said when we found these things. They said, look, there's the Themis family right there. We know about Themis family. We're asteroid people. Themis family is a 300-kilometer asteroid that was smashed by a collision probably about 2 billion years ago and has many fragments flying around in this region. Look, 2 of your main belt comets are in the Themis box, and therefore they must be pieces of a smashed asteroid that was probably watery and big enough to differentiate. It had a metal core, a rock mantle, and watery rocks floated up to the surface, and you've just got some watery rocks. Maybe. The third object, well, it's not quite in the Themis box, but it's nearby. Maybe it kind of diffused out of the Themis box. Then we found this object, 2008 R1, which is nowhere near the Themis box. But you could say, well, conceivably, this body was scattered out of the Themis box a long time ago, and it's diffusing in orbital element space, and that's just where it is. And then most recently, we got this object down here in the inner asteroid belt, which is really nothing to do. There's no easy path from there to there in the asteroid belt. So it's a big mystery, but we have these 5 mass-losing bodies in the asteroid belt. A very strange thing. Most of them discovered quite recently. So here's the most recent one, just for your entertainment. This object was discovered by a military telescope in New Mexico and was just, as they do, just reported as a comet with no special remarks about it. But I noticed immediately that its orbit is in the main belt and in the inner main belt. So I got my buddy Jim Annis to take pictures of this thing that night from a telescope in Arizona, Kitt Peak. And you can see it's a very strange morphology. It's a diffuse smudge of light with the hint of a nucleus, a persistent point at the top end there, and also a hint of a light bridge between the nucleus and the main thing. And a deeper image looks like this. So here's that nucleus connected by a little light bridge to the main tail of dust. Comets don't look like that. The nucleus is usually inside the coma because it's the immediate proximal source of the coma. And so this picture motivated, we're building up the chain now, this picture motivated a picture from Space Telescope. And we have a bunch of these now. And this is a point that we can see just about in the ground-based data. Here's that light bridge, and then here's this X stuff. This is a star trail, but everything else is real in here. This structured coma of dust. And, you know, I don't know what that is. So my guess is that it's the result of a collision between two previously unknown asteroids. And these are streamers of debris coming out of this thing. Like, imagine chucking a brick into a swimming pool. The splash pattern is not a perfect symmetrical cone. You see ribbons of stuff that come out. So perhaps these ribbons are associated with the impact onto this side of the primary nucleus. This thing is small. It's about 140 meters across. And we see in the data evidence for other things spread through here. And we're following them. And the most amazing thing to me is that we've taken pictures of this now since January with Space Telescope. We keep going back, and we'll keep going back until the summertime. And I would expect these things to move away from the nucleus because radiation pressure is pushing them away. It's over here. It's down in this direction. But in fact, what's happened so far is the structure has become smaller. So the whole thing is apparently collapsing. Now, I think it's just because the object's getting further away. But the speeds in this are tremendously slow. They're very, very tiny speeds, sub-meter per second velocities. It's a very, very strange object. And all sorts of religious nutcases write to me and say, you know, this is the mark of God, or this is all this stuff. A very interesting object. What? I've had the Star of David. My name is David, and my first name has got a Jew in it, so I've had that one too. I got the whole thing. There are many, many crazier ones than that, but no death threats yet. So what about the main belt comets? I'll just finish up with this. Where do these main belt comets come from? It's clear, I think, that we're seeing a population of bodies with different intrinsic natures. So some, like 133P, are hard to explain by anything other than the sublimation of water ice because they're repetitive. They keep coming back. They know where they are in the orbit. They know where the sun is somehow. So they're icy. Others may be collision clouds. There may be some other explanations too. Could they be captured from the Kuiper belt? So dynamical experts say no. Yep, the best people have tried to integrate comets from Kuiper belt and capture them into the asteroid belt. Cannot be done now, basically because the Tisserand parameter is wrong. It has to, it's bigger than 3, less than 3. Tisserand is conserved during a capture. So that doesn't work, at least now. Could they have formed in place? Yes, they could. Could we trap ice in the main belt, even though it's quite hot there? Yes, we could. The evidence for that is very clear and very strong. I'll mention that in just a moment. Could they be captured from the Kuiper belt at an early epoch? Well, yes, they could. And how would you do that? Well, the answer is Nice model. So Nice model people have said, unfortunately too late to explain these objects because we discovered them first, but Nice model people have said, yeah, we could capture stuff at this time when the Kuiper belt is scattered into the outer asteroid belt. And these objects that come from the Kuiper belt would be, cryogenic bodies that would be full of ice. Maybe that's what we're seeing. So I think the door is open to that possibility, but there's no particular reason to think that they come from the Kuiper belt. To me, Occam's razor suggests that they come from where we see them, the outer parts of the asteroid belt. And I say that in part because of pictures like this. So to me, the main belt comets were a big thing. I thought, hey, that's really, really cool. When I told my meteorite expert colleagues about that, their reaction was, yeah, water in the asteroids, big deal. Tell us something new. And that's their reaction, of course, because many materials from meteorites from the outer parts of the asteroid belt are hydrated. So this brown stuff is serpentine. This is a mineral that forms in the presence of liquid water. And so we have all sorts of evidence for the past presence of liquid water in the asteroid belt in meteorites. And it's very firmly established evidence. It's not a contamination, it's quite abundant, and so on. So I think we're seeing different things. The meteorite people are saying there was once water and it melted and reacted with the rocks to make the minerals we see. We are saying, at least in the case of 133P, water ice is still there. It never melted and reacted with rocks because it's still there. So somehow, in the history of the asteroids, it must be possible for ice to survive in some places while being melted and chemically reacted in others. But the basic picture is the same. Another thing I really like to talk about is this object, because it's kind of a field bridging object. This is a meteorite, about 10 centimeters across, that fell in Texas just over 10 years ago in a place called Monahans. And it's called the Monahans chondrite. And it's special because it fell near some teenagers playing basketball. And they weren't just ordinary teenagers, they were special teenagers who stopped playing basketball and ran over to this thing. They saw it hit the ground and bounce. They ran over to it and picked it up in a baggie, which they happened to be carrying with them for some reason. And they immediately kept this meteorite in the baggie and sealed the thing, thereby preventing any possibility of contamination from their fingers, oil, water, breath, the whole thing. Then, even better, instead of taking it home and putting it on the shelf, they sent it to Johnson Space Flight Center, to one of the world's experts in the study of meteorites called Zelensky, Mike Zelensky, who, being a good geologist, hit it with a hammer and broke off this piece right here. So you can see the black fusion crust here and the relatively light interior that was not burned by the passage through the atmosphere. And then he put a microscope to it. And a microscope picture is shown here, not very distinct on this screen, but you can see square-looking things up here. There's a kind of a square-looking thing there. There's a whole bunch of squares, and they're cubes, and they are, in fact, salt. So these are crystals of sodium chloride in the meteorite, and the age of the sodium chloride has been measured by rubidium-strontium decay dating as being consistent with the age of the solar system. There are other methods of getting the age, and they give consistent results. It's very old salt, age of the solar system, basically. And Zelensky told me this great story. So I met him for the first time in yet another one of these talks like a month ago in Texas. And he said, yeah, once I realized I got salt in the meteorite, I did what every geologist had to do. And I said, what was that? He said, I licked it. So there's a man in Texas licking cosmic salt for a living, which is a good thing. Now, the story is even better. Inside this salt crystal, which is roughly 1 millimeter across, there are little shapes. Here's one of those little shapes shown magnified. This one is a tiny one, 5 microns across. This is a pocket of salty water. It's liquid brine sitting inside the salt crystal. And if you look inside the salty brine, you see this thing called V. V is a bubble. And V is a little bubble of gas that sits inside this liquid and moves around as a result of Brownian motion. The molecules in the liquid are bombarding the bubble and pushing it around. So I just mentioned this. I give this little spiel because I think it's really cool, actually. It's totally not new research, okay? It's a decade old. It was unknown to me until recently. It's unknown to almost everybody when I give a talk for some reason. I think because science basically is much too specialized. We just don't know what other people are doing. But you have to admit, whatever your background, is a really fantastic result. Here is a bubble of gas inside a liquid brine pocket, inside a salt crystal, inside a chondrite, a meteorite, that was inside an asteroid that got smashed, sending these fragments to the Earth sometime in the recent past. So if you have any doubts about the presence of liquids in the outer asteroid belt, just look at things like this. Very, very direct evidence. The salt is there because there was some lake or something that evaporated into space and became saltier and saltier. Salt crystals formed, and then the water was reacted or lost or maybe frozen. Okay. Here's the bubble. If you look there, you can see the thing moving. Again, the projector is not that good, but you can just about see this little bubble bouncing around because of Brownian motion.
Do you know what it's a bubble of?
I certainly don't, and I asked him, and he didn't. He said that he didn't. But more research has been done that's about to come out. So, for example, the deuterium-hydrogen ratio has been measured by Zelensky and others in this liquid, so that's important. Now, we care about that because, for a number of reasons, watery asteroids have this extra heat source from chemistry called serpentinization. So when water reacts with rock, it's like making concrete. You get a lot of heat come out, chemical heat. And that heat, in principle, can play an important role in the heat budget of an asteroid. We also know from the ocean, and this is a case where there's heat coming out at the bottom of the ocean, we also know that when you have water and energy, and minerals, food, we get life. I mean, living things occur there. And so it does, I mean, because we're in the SETI Institute, I want to just mention this idea that we are looking at objects where all the ingredients existed, probably at the right time for life to begin. So in the first 100 million years, the Earth was a hostile place for life. It formed hot, it was molten in the beginning, it took a long time to cool down. Life probably didn't get a start here in the first 100 million years. But the asteroids had a heat pulse from aluminum-26, iron-60 that lasted, the half-life is 1 million years. So after a few half-lives, the heat pulse is gone. And then they just cool on the conduction cooling time, which for a 10-kilometer body is close to 100 million years, 50 million, 100 million years. So they're cooling down towards freezing. They never reheat, they just cool down. But during that time, they could have melted ice, chemical reactions like serpentinization that generate heat to keep things going, and production of the precursor molecules to life. And then, because the asteroid belt, we know, is cleared due to the emergence and slight inward encroachment of Jupiter, the asteroid belt is cleared of most of its mass in early times. All of these asteroids, which represent, 50,000 different experiments for the origin of the chemical precursors to life, all these things are scattered through the solar system. And they go off and they hit Mercury, and they die, and they hit Venus, and they die, and they hit Mars, and they live for a little while because the climate on Mars is pretty good in the beginning, and so bugs get going there, and they hit the Earth, and then eventually they become us. So, through these observations of different icy things in the solar system, we start to see connections that look pretty interesting. Not only to between the different populations, but also to this question of the origin of life. And it's no surprise, actually, that there are meteorites that contain very important amino acids and other chemicals needed by life to get going. So I think all the ingredients are there. I'll stop.
Dave, I'll just ask the first question. We've now got a mission heading out to a Kuiper belt object, and we've got a mission heading to the asteroid belt. Can you tell us what you're most excited about when Dawn reaches Vesta and when New Horizons reaches Pluto? What will you be looking out for in the results?
Well, actually, I think, certainly at the present time, as much science or more science comes from the ground-based telescopic data. I mean, the spacecraft missions tell you a fantastic amount about the individual objects which are visited. But what I want myself, and what I try to give in this talk, is broad perspective. And that actually comes mostly from telescopes on the ground, because with telescopes you can see a broad population, you can discover a population. You can't really do that with the spacecraft. So to answer your question, that was a political spiel. The mission to the asteroids, Dawn, will be able to do some geophysics, and it will be able to do some high-resolution surface spectroscopy at a place, Ceres, where we think there's water ice. Maybe not exactly at the surface, maybe it's present, exposed at the poles, certainly underneath the surface. And so I'm looking for indications of the water abundance, basically, on Ceres. I think that'll be quite interesting. The Pluto mission, yeah, it's going to a Kuiper belt object. It's going to a big one, so it's lost all many of its traces of its original nature. I mean, it's a round body. It's thermally evolved in the interior. I'll be interested to see if it's active, for example. Is there any evidence for this active launching of material above the surface of Pluto as we saw on Triton. Basically, high-resolution stuff that you can't get from the ground is what you'll get from these missions.
Dave, a year or two ago when I heard you speak about the discovery of the main belt comets, you gave a fairly strong impression that you thought at that point that the issue of the origin of the Earth's oceans was solved. And I don't sense in today's talk quite that degree of assertiveness or certainty.
It's because I'm jet-lagged and I have a sore throat. No, it's because as I get older, I get wiser. So what happened? In the past, people assumed that this late veneer of volatiles, as you know, was delivered from the comets. The first measurements of D to H in the comets changed people's minds because D to H in the measured comets is 2 or 3 times higher than it is in the oceans. So if you just melted the comets, you would not have the D to H isotopic composition that we see in the oceans. And so people started to look for other sources. And then Morbidelli and other people looked and said, yeah, you know, in fact, Kuiper belt is not such a good source for the volatiles because from the Kuiper belt, the Earth is this, micro target, a tiny little dot, hard to hit from the Kuiper belt. Whereas if we're in the asteroid belt, Earth is a much better target. And that makes sense because we are hit all the time by things from the asteroid belt called meteorites. So the pendulum swung a little towards the asteroids, and in fact to the outer belt, where we see objects like 133P, the main belt comet. So that all is consistent. Furthermore, there are measurements of D to H in various materials in meteorites from the outer asteroid belt that are spread over a wide range, but encompass the values that we see in the terrestrial oceans. So that's consistent, I think. But it's not a proof. And in fact, if you go back to the cometry measurements of D to H, one of which I was involved with, those measurements are, super, super tough measurements. And even as presented in the journals, are close to 3 sigma measurements. And, as any experimentalist will tell you, at least half of all 3 sigma results are false. Completely negating the meaning of 3 sigma, but that's actually the case. So the observational constraint on the D to H ratios in comets is a very limited value, I would say, at the present time. And so the reason for this re-examination of the origin of volatiles and the finger pointing from comets more towards the asteroids may be a specious reason. So I don't know where the water came from. My gut feeling is it came from a whole bunch of different places, some from the asteroid belt, some from the comets, which we now associate with primarily the Kuiper belt. The best reason for thinking there must be a cometry source is actually not the water, but it's the noble gases. So the Earth also picked up noble gases somewhere along the line. And we think that the best way to trap noble gases is at low temperatures in porous, spongy, amorphous ice, which one would tend to find only in the Kuiper belt and beyond. But I think the door is open to all sorts of things.
So following up on the Nice model prediction that we'd lose the Earth and then the modifications that address that problem, just wanted to dig a little deeper. What was the mechanism for losing the Earth and how was that addressed?
The mechanism for losing the Earth was just simply found to be unstable as a result of this shaking when Jupiter and Saturn go through the resonance. How do they address it? I honestly don't know.
Okay, so just an orbital instability which ultimately results in the Earth completely leaving its orbit?
Yeah, I mean the same thing that destabilizes the Kuiper belt, which is out there 30 AU or something, also destabilizes, in the original models, destabilized the terrestrial planets too.
Okay, thanks.
But what they did to fix that, I think you should read the paper and see if you believe it. Yeah.
I noticed that you had a table where the Oort cloud was forming fairly early in, like 5 to 20 AU. And so obviously it's much larger, it's at a much larger distance. I presume that was a result of Jupiter and Saturn moving in, but I was curious what constraints that puts on that whole idea of the outer planets moving in and everything like that.
So I think I remember the slide you're talking about.
Yeah.
The idea is that the comets, which we now find in the Oort cloud, originally were in small heliocentric orbits where we see the giant planets. And so most of those objects, many of those objects were grabbed to build the giant planets. But those that were not captured into building the body of the planet were ejected, were launched outwards. So the 5 to 20 AU is just some estimate of the initial range of distances where the giant planets sat when they formed before this migration phase moved them to their present locations. So it's probably a slight overestimate of the range of distances from which the Oort cloud comets were derived, because Jupiter is so good at ejecting bodies at high speed, it tends to eject everything faster than the escape speed from the solar system, and very little of that gets into the Oort cloud. Whereas Uranus and Neptune are less massive, have smaller escape speeds, and are better at launching particles that can be deflected and captured into the Oort cloud. So the probable range of distances for most comets in the Oort cloud is smaller than 5 to 20, the outer part of that range, with some small component from the inner regions. And that reminded me of another mistake in Oort's paper that was seized upon by Kuiper. In his paper, Oort, for some reason, says that the Oort cloud comets are basically asteroids, is the word he used, asteroids from near the orbit of Jupiter, which I think now people would not, by and large, believe. That was jumped upon the next year by Kuiper, who was Oort's grad student in a previous life, who wrote his own paper in which he said, well, it can't be right, because then there'd just be rocks, and in fact they're all icy and we see tails, and he was right about that. And that's where he wrote about what has come to be called the Kuiper belt. But if you read that paper, what he predicts is that the region where we see the Kuiper belt would now be completely empty, because he believed, along with many other people, that Pluto was an Earth mass body that would scatter everything away from it in its vicinity and literally carve out a zone that would be devoid of all the things that we now know are there. So Kuiper's belt was an anti-prediction. And I think he was motivated in part by this mistake made in the Oort paper a year before.
Dave, I'd like to go back to whether there's any predictions for the Nice model.
Yeah.
I know very little about dynamics, but I think I know that the moon had a late heavy bombardment at a particular time, which it could be a consequence of the Nice model. The question is that a prediction, or was that one of the parameters that went into constraining the model?
Right. Good one. So the Nice model is one of the things the Nice model is, the late heavy bombardment is one of the things the Nice model is most wanted to fit. So their assumption is that there was a late heavy bombardment at about 3.8. And the puzzle is, how could the solar system save up all this debris for so many hundreds of millions of years and then suddenly launch it at the moon 700 or 800 million years after it formed? So the Nice model that you saw has been tuned so that the planets jiggle around and drift towards resonance crossing at just the right moment. Yeah? So the initial parameters are selected to make that happen. And one of the issues with Nice model is if the late heavy bombardment happened at another time, you would simply pick a different set of parameters and get the resonance crossing at a different time. So things that you can change include the mass of the Kuiper belt, the degree of dynamical excitation of the Kuiper belt, because that affects how they interact with the planets, the state of growth of the Kuiper belt, the distance between the Kuiper belt and the outermost planet, and so on. So there's a whole bunch of parameters that go into making this model give the right answer. But it doesn't predict the late heavy bombardment, it fits it. And there is this drift, you might have noticed in scientific language, where models are said to predict things that are already known. I'm not sure if you've seen that in print, but I've seen it so many times. I mean, if you predict something that's already known with a model, that's actually called a fit. I mean, use the right words, yeah? So it's a fit to the assumed late heavy bombardment.
basic question, Dave. So the outer planets were drifting out or migrating out in our solar system, but we now see exoplanets that are very close into their star. Perhaps we're prejudiced in our current ways of detecting exoplanets, but it appears that they're a lot in very close to their star. What's the basic reason why they might migrate inwards to their star, whereas we might have migration outwards in our solar
Well,
system?
we think in the solar system that Saturn, Uranus, and Neptune went out, and Jupiter went in. So if you had a one-planet solar system ejecting comets off to infinity or to the Oort cloud, the one planet would go in because it has to be the source of the energy and angular momentum of the stuff being launched out. But solar system is a connected set, so you have several planets and they can interact. And it turns out that the source of the angular momentum is Jupiter. So Jupiter goes in. But because Jupiter is so massive, it doesn't have to go in by much to supply all of the energy and angular momentum to launch all of the comets to the Oort cloud and beyond. So the estimate is that Jupiter might have moved inwards by half an AU. And when it did that, was responsible for some dynamical disturbance in the asteroid belt just inside it. And the outer planets went out by substantially larger distances. Now, in the external systems, the extrasolar planetary systems, other things may be going on. So we think the planetary migration in our system is this object-by-object scattering of bodies. At the phase when a planet is growing and when the massive disk of material still exists around the planet, there can be these very strong torques between the planet and the disk. And those torques just drive the planets in like a conveyor belt, sending them in towards the star. So the hot Jupiters, which is what you're talking about, perhaps were driven in by some interaction with a massive disk at or about their formation time. Yeah.
I have no further questions. We have a special SETI pin to present you for your fabulous talk today.
Nope.
And
Thank
if
you.
you'll join me.
Thank you.